Today we're going to take a look at section 7.2, which is operations on decimals. So we started with decimals and looking at them last time, talking about their relationship a little bit to fractions, having some diagrams, decimal square diagram, and so forth. And we're going to talk first of all today about addition and subtraction. So addition and subtraction works in the following way. We will line the decimal points up, and we will add and subtract as with whole numbers. And we're going to do that with this numbers 4 and 33 hundredths, plus 3 and 26 hundredths. And then we're going to talk about why we do what we do and why it works. So what we're being told that we will do is we will line this up. And lining them up meaning that the decimal points are in the same location, like vertically. And then we add like we do with whole numbers. And if you've taken number theory, you know we have multiple, options of how to do the addition. The standard algorithm starts on the right-hand side. So 3 plus 6 is 9. 3 plus 2 is 5. And I bring my decimal point straight down. And then 4 plus 3 is 7. Okay. So that's what the algorithm is, the way in which we do it. The reason it works is because of fractions, or place values more specifically. So I'm going to take the number 4 and 33 hundredths, and I'm going to break it up into 4 plus 3 tenths plus 3 hundredths. You could do 33 hundredths as well if you wanted to do it that way. It would be all right. And then I can do the same thing here. I've got 3, I've got 2 tenths, and I've got 6 hundredths. Okay, so that's what the expression would look like in expanded form with decimals, turned into fractions, I mean. So, and then we can pair them up, right? So the parts that would match, so the 4 and the 3, those are 7. And then I have the other parts that have the same denominator, so 3 tenths and 2 tenths is 5 tenths. And then 3 100ths and 6 100ths is 9 100ths. And then putting that back into the decimal form, I would have 7 and 59 hundredths. So when we line them up, that's what we're actually doing, is we're lining up the same fractional piece, the piece that's in the same placeholder value. So that's why we're adding the 3 and the 6 together in the hundredths places, because they're both fractions with denominators of 100 and so forth. Okay? So that's addition. Subtraction, of course, is the same sort of thing. So we're going to do an example with subtraction that has a little bit of context. A stock price dropped from $63.28 per share to $27.45 per share. What was the loss on a single share of this stock? So it is a subtraction problem. We're trying to figure out how much money we lost per share of stock. So I have 63. I have my decimal point, 28. And then I'm subtracting 27 and 45 hundredths. So our standard algorithm says that we go to the right-hand side first, and we subtract down. So 8 minus 5 would be 3. But as soon as we move into the tenths place, there's a problem, right? I can't really take, 4 dimes away from 2 dimes. That's what that place value is dimes. So I have to exchange the money, right? I have to go take one of my dollars right here. This $3 becomes $2. And I take that dollar and turn it into 10 dimes. Now I have 10 dimes plus the original 2 dimes. I have 12 dimes. And now I can take away 4 dimes from 12 dimes. So 12 minus 4 would be 8. And I'm going to bring my decimal point down. And I have the same problem happening sort of again. I have 2 $1 bills, and I can't take away 7 $1 bills. So I come over to the 6, which is 6 tens. So for my 6 tens, I trade one of my tens away to become 10 ones. So now I will have 10 ones plus the 2 ones I already have is 12 ones. So 12 ones minus 7 ones would give me 5 ones. And then finally 5 tens minus 2 tens would give me 3 tens. So with a dollar sign in the front, I have $35.83. And we exchange money all the time. I know less these days than once upon a time because we swipe cards a lot too. But the idea of exchanging money and making change is still a concept that we should be very familiar with. So it works really nicely to talk about that referencing with decimals.
Dr. Hans?
Yep.
On the side previous, if we have, like on the test, explain why this works.
I would say explain why this works in reference to fractions or something like that.
In reference to fractions, not
I would
its
tell you.
values.
No, I would tell you how I want you to explain it.
Okay.
Yeah. So I wanted to show you the connection back to
Show it
fractions.
like that?
Yeah,
Okay, and that would
absolutely. You'd still have to use some words
Yeah.
around it because anyway, anytime we say explain, we mean with words. Which you guys did a great job on that, by the way, on the test. Usually when I have students doing explain, I have several students every time not explaining in words. And you guys did a really good job on the test of using your words to explain. So I was very pleased with that. Yeah, so explain is always going to mean with words, but you could do this as the background to the words for sure. All right, so addition, subtraction. The next one would be multiplication. So multiplication, multiply as with whole numbers. And then you count the number of places after the decimal point in all of the factors, all the numbers you multiplied. And this will be the number of places after the decimal point in your product. Probably the most common error students make when they multiply decimals is that they try to move the decimal point down the way they do with adding them or subtracting them. They just shift it all the way down, right? And so if we're using this method, here's what we have. So we say 7 times 3 is 21, and so what you might commonly see a child do is to put the decimal point between the 2 and the 1. But what this is saying that we need to do is we need to count how many of the non-zero numbers, or I didn't say it that way, right? How many of the numbers come after the 0 and the decimal point? So in this case, there'd be 2 numbers, the 3 and the 7, so 2. And then the decimal point goes 2 decimal places after. There will be 2 values after the decimal point in your answer. So I still have 1, 2 values after my decimal point to match. But I want to show you why it works in terms of fractions. So if you take the number 3/10 and you write it as a fraction, it's 3/10, right? And if you do the same thing with 7/10, it's 7/10. 3 times 7 is 21, and 10 times 10 is 100. It's 21 hundredths. And sure enough, there's those 2 decimal points that we expected to see happening, or 2 values we expected to see after the decimal point. And then our last operation is division. So with division, we make the divisor a whole number by moving the decimal point in the divisor and the dividend an equal number of times. Then we divide as with whole numbers. So why does this work on the next page? So you have 75 hundredths divided by 5/10. So we're going to write this in a division house. That's what my kids call it, a house. So I have 75 hundredths underneath the division bar, and I have the 5/10 on the outside of the division bar. I need to change the 5/10 on the outside so it's a whole number. So I will move the decimal point 1 place, which also moves it 1 place between now the 7 and the 5. And there will be a dot between the 7 and the 5 up on top of the division bar. So thinking about division now, how many times does 5 go into 7? 1 time. So 1 times 5 is 5. 7 minus 5 is 2. And we bring our next 5 down. 5 goes into 25. 5 times. 5 times 5 is 25. I get a remainder of 0, so I stop. And my answer is 1.5. Okay. That, I think, is maybe the most mysterious. Well, the multiplication one's just as mysterious looking, counting the number of decimal places and plopping a decimal down, shifting things over, and all of a sudden it's in the right place. Like, why does that work? Well, no surprise, it works because of fractions. So if you consider writing this as a fraction, and I'm going to write it as a fraction like this. There's other ways we could do it, but this is a really nice one. So that's the same division problem, right? Just written in fraction notation? Sure. And we tend to not like to have decimals and fractions intermixed in the same problem. It's sort of like this cardinal no-no, right? We don't do that. Well, what's happening then, if I try to get the denominator specifically, because I want to show you how it applies to the other algorithm. If I try to get the denominator so that it doesn't have a decimal in it, I'd need to multiply the denominator by 10, right? That would shift my decimal place. So if I multiply the denominator by 10, what literally happens is that this decimal place moves 1 to the right, giving me the 5. And whatever I do to the denominator, I also have to do to the numerator, so the decimal in the numerator also moves 1 to the right, giving me the 7.5, which is what I really did in my division problem already. I really did 7.5 divided by 5 like that, once I shifted the decimal points around. So what I'm really doing is I'm really just multiplying both the divisor and the and what I'm dividing by, the quotient, the divisor and the dividend, that's the words I want, by the same value, 10. That's why it's shifting decimal points, and it works okay. All right, scientific notation. Do you guys remember doing scientific notation? Do you do it in Dr. McWilliams' class? Is that something you guys ever cover over there in any of the science class over there? No? Okay. So scientific notation is a way of expressing really large or really small values in a concise way. So it's not just something we're going to randomly take a number and write it in scientific notation, but there are values that are written in scientific notation because of certain features of them. So the basic form from scientific notation is a times 10 to the n. The a value is between 1 and 10. It could equal 1, it can't equal 10. So it's going to be not a 1, it's going to be a one-digit number, right? I mean, a single-digit value. It's not going to have a tens place. And then n itself is an integer. So since it's an integer, it could be positive or negative or technically 0. So n could be an exponent of 0. It's not a very exciting one, but technically it works. So scientific notation has the ability to change really large values like the distance between here and the sun in meters, or really small values like the distance between, electrons inside of an atom, and write them in a way that doesn't end up taking lots of zeros. That's really what we're trying to avoid, really long digits of numbers, right? Like that's not cool. So there are two different ways that we want to be able to move within scientific notation. We want to be able to take something that's in scientific notation and write it in standard form. And we want to be able to take something that's in standard form and write it in scientific notation. And there's more than one way to sort of write out what that looks like in terms of how we shift the numbers around. This one is the first one. We're going to do standard numerals to scientific notation. And we're going to move the decimal point to create a value between 1 and 10. We're going to count how many times we moved the decimal point, how many shifts we made, or how many jumps we made. And then this right here is the part that may look a little different than what you've seen before. I absolutely don't like talking about moving the decimal point right or left and it becoming positive or negative. The reason that I don't is because then I have to remember, am I going between scientific and standard, or am I going between standard and scientific, because it shifts the direction of whether I'm going left or going right. So I find this to be an easier way to think about it because it works in both directions. So the way that I talk about it is that a positive exponent indicates a large number, and by large, it's all relative, right? By large, I mean bigger than 10. That's large, okay? And then a negative exponent indicates a small number, and by small, I mean smaller than 1. So anything smaller than 1 is a small number, and it involves negative exponents. Anything larger than 10 is a big number and involves positive exponents. Okay, are you ready to try one? Cool. My number is 298,000, and I want to put it into scientific notation. So the first thing that I do is I need to put a decimal point somewhere so that it creates a number between 1 and 10. where will my decimal point go between the numbers 298000? Perfect. So between the 2 and the 9, I will have a decimal point. Now going back up to the original problem, that's here. And the original decimal point would have been at the end of the zeros. So the thing I need to do next is I need to count how many places I moved the original decimal point to, here, to get over to my new decimal point location between the 2 and the 9. So if I count, I moved it over 1, 2, 3, 4, 5 places. Everybody good so far? So I know that this is times 10 to the 5. If my number is a big number, it's positive 5. If my number is a small number, it's negative 5. Is my number big or small? It's big, right? This is a big number. It's bigger than 10. So I have a positive exponent. And I'm done. Going the other direction, almost exactly the same steps because of how I've described it. We're going to move the decimal point the number of places indicated by the exponent. A positive exponent is going to give me a big number, and a negative exponent is going to give me a small number. So we're going to do 3.2 times 10 to the negative 5th. So let's first look at that exponent and decide, is my number going to be big or is my number going to be small? It's a small number. So right now, I can move the decimal point to the right, or I can move the decimal point to the left, but I need to move it in the direction that gives me a smaller number. So it's going to go left. So originally, I had 3.2, and I need to move it to the left. I'm just going to put a bunch of zeros on here for the moment. And how many times am I going to move it to the left? 5. 1, 2, 3, 4, 5. So I end up with, come on, a 0 and a decimal point, 4 zeros, and then 3, 2. And my negative exponent did create a small number. So far, so good? Okay. This next problem is actually given to us in scientific notation. Okay? And it wants us to solve it. You simplify it, whatever, combine like terms and all that good stuff. But you do not want to change this into standard form. That is so not productive. It's not that it's not possible, it's just that it's a lot of work when it's not necessary. So the cool thing about multiplication, and we do this back in chapters 3 and 5 in number theory, is that it's commutative. So multiplication has the ability that because all this is multiplied. It's 8 times 10 to the 12 times 6 times 10 to the 15th, right? It's all multiplied, which means that I can interchange all the multiplication in whatever order works best. And for this one, it works best to multiply the 8 and the 6 and the 10 to the 12th and to the 10 to the 15th. So what's 8 times 6? 48. And then 10 to the 12th and 10 to the 15th is what we did back in chapter 6 with properties of exponents. What do I do with the 12 and the 15? I add them, right. 12 plus 15 is 27. Am I done? Not quite. What's wrong with this number as it is right now? Yeah, the 48 is bigger than a one-digit number, right? It's not got just a units digit. And I can't have a units digit and a tens digit. It's bigger than 10. So what number should it be? Yeah, I want it to be a 4.8. I'll use the x for multiplication here to keep it off because I got a decimal point with a 4. But the question is then, what do I do to the 27? Yeah, it's going to be a 28. So Danielle, you answered that really fast. How did you know that I needed it to be a 28 and not a 26?
Because you moved it to the right.
Okay, so thinking about the rights and the lefts, it's bigger, right? 48 was a big number. So I added 1 to it. The exponent became bigger. Yeah, that's exactly right. So I have 4.8 times 10 to the 28. Very good. The last part of this section is about rounding. So we're going to talk about rounding to the nearest blank. So it's blank because it can be anything, right? It could be the tens place, it could be the hundredths place. It doesn't really matter. All the rules are the same no matter what place I'm rounding to. So as I'm rounding, what I need to do is I need to find the location that I'm going to round to. And then if I have a 0 to 4, it rounds down, and a 5 to 9, it rounds up. So this section in your book's a little bit frustrating because it likes to say round and not tell you what to round it to. I find that frustrating. I need a little bit more explicit directions myself. The cool thing is, from your perspective, is that means you get to decide. So if you're rounding something, you can round to the tens place, or you can round to the hundredths place, or, I mean, you get to pick if it doesn't tell you. So we'll get to an example about that in a minute. Front-end estimation is a very interesting rounding strategy, or estimation strategy, not rounding, an estimation strategy. What it does is it uses the first value, or maybe the first couple of values, and then it rounds off. Now, rounding off and rounding are not the same thing. Rounding off means that after that first value or that second value, it just makes everything else zeros. Okay? It doesn't go up for anything. It just stays everything else zeros. It's kind of like rounding down all the time. So rounding off is the same as rounding down all the time, no matter what comes next. So if we take a look at this example, 203 and 651 thousandths, we're going to round as it's specified. So the first one says to the nearest hundred. So what number is in the hundreds place? A 2. So I've got 203.651. This is the value that I'm trying to round. So what I do is I go to the place value next to it, and it's a 0. 0 to 4, I round down. Well, what does rounding down mean? Well, it means that the value that's got the blue or the purple line underneath it and everything else simply goes down to 0. The 2 doesn't change. 2 stays the same and everything else becomes zeros. So I'm just going to write it as 200. No real need to write the decimal point with a bunch of zeros after that. 200. The next one is to the nearest hundredth. So what value is in the hundredths place? Yep, it's a 5. And again, I go to the place value after it. The place value after it is a 1. 0 to 4, I round down. So what will the 1 become? A 0. So I end up with 203.65. Because the number after the 5 became a 0. And then it says to the nearest unit. So what number is in the units place? A 3. So look at the value afterwards, and it's a 6. Finally, something that's not just turn it all into zeros, right? 5 and up, we round up. Well, what does that actually mean? Well, it means that the value in front of it will actually change this time. So instead of saying 203, it's going to become 204. Everything after it still becomes zeros, but rounding up actually affects the place value I'm rounding to. And I get 204 on this one. Okay, example 6. This is like straight out of your book words. Use A, rounding, and B, front-end estimation. And it doesn't tell you anything about place value, right? So you get a pick. Now, let's think about it. If we get a pick, what's the nicest thing to round to? Tens place is even nicer. Ones place is pretty good. Tens place is even nicer, right? Because if I'm rounding with the tens place, everything else becomes zeros. I'm getting a whole bunch of zeros when I'm done. Okay, so let's take a look, and we'll do it to the tens place, and then we'll do it to the ones place just to see how it changes things. Often it doesn't change it a whole lot in terms of values in the end, which is also very interesting. So taking a look at the directions, it says use the rounding to estimate. So we're not going to do the problem and then round the answer. We're going to round the problem to find the answer, right? The whole goal with rounding is to make the computation easier to do. Okay, that's what our goal is here. So if I'm taking this right here, 89 and 47 hundredths, and I'm looking at the tens place, and I'm looking at the 9, what does that 9 tell me I'm going to do? I'm going to round it up. So what will the 89 and 47 hundredths become? 90. Over here, I've got the 3, and I'm looking at the 2. So what will the 2 do? Round it down, which means that the 2 and everything after it, they get zapped, and I just have a 30 here, right? And if I subtract, I get 60. Rounding to the nearest hundreds is what I'm doing right now, which means that I only have a hundreds place and everything else is zeroed out afterwards. So the reality is, maybe I should say it this way too, this number 32, it's between 30 and 40. Are you guys with me on that? So what happens when I round to the hundreds place is that I am going to always get the answer of 30 or 40. The question is, which one is it closer to? Well, 32 is closer to 30. That's why it becomes 30. Whereas 89 is closer to 90 than it is to 80. That's what rounding's really doing. All these sort of rules behind there, but we're really just trying to get the closest tens that we have. All right, so that's sort of part A, which was the rounding part with tens. I'm going to do the tens as well for part B so that we can compare and see how it works. Because we haven't done a front-end estimation problem before, and that's not always one that you've seen before you see me in this particular section of material. So front-end estimation simply takes the first value and it zeroes everything out. It doesn't care what the next values are. Rounding cares. Front-end estimation doesn't care. So my 89 becomes 80 and my 32 becomes 30. And I get 50 when I subtract. I don't necessarily get the same thing, right? Sometimes I would, but on this problem I don't. So that one would be actually front-end estimation. And then it doesn't say written part C, but this is the C, right? C says, then perform the computation. So let's do part C. So part C is to take the 89 and 47 hundredths and to subtract 32 and 16 hundredths. So standard algorithm then, start on the right-hand side. 7 minus 6 is, good, 4 minus 1, 9 minus 2, yep, and 8 minus 3, 5. So it's 57 and 31 hundredths is the actual computation. Okay, so on this one, rounding ended up being better, you're right. Now, just say, for instance, that you did this problem, and a couple of you said, let's round to the nearest ones, or that's what you're sort of considering to begin with, ones or units place. You definitely can do that. It doesn't hurt anything. Let me show you what it would look like if you had done it. It would be equally right. So if we looked at the units place, then in the first part of the problem, the 89, we'd be looking at the 9. So looking at the 9 and going over to the 4, will this number stay 89 or will it become 90? It would stay 89 because 0 to 4, we stay the same. So we would get 89. And then on my second value, the 2's place, or the 1's place has a 2 in it. And then the 1 next to it, right, we would consider that for the number 2. Does this stay 32 or does it become 32? 3. Yeah, it stays 32. And we would subtract the 32. So it's not that this is a terribly hard problem to subtract. It's actually friendly in the sense that I don't have to do any borrowing. But obviously, subtracting a 2-digit number has twice as many steps technically as subtracting the 1-digit number that it looks like it is in the units place for the tens. If I did the units place with the front-end estimation, the 89 would actually be 89, and the 32 would be 32, because everything just zeros automatically. So on this one, front-end estimation doesn't look any different than rounding at all. They actually give you the exact same value of 57. Whereas when we did it with the tens, it was not the same value. So it just depends on the problem. All right. Our last example we're just going to talk about, and we'll save it for next time to actually do it. But it's a very interesting kind of problem and question. This is one of those that came, I think it's still in your book in Part C. But a student tries to calculate 0.999, so 999 thousandths, to the 10,000th on a calculator. And he finds the answer to be 4.5173346 times 10 to the negative fifth. That's a very small number, right? Because the negative 5 on that scientific notation, right? It's a small number. But the student wonders how it could be possible that a number like 0.999, which is so close to 1, so close you might have thought it was the biggest number less than 1 on the last assignment, right? It's really close. How a number so close to 1 raised to a power could result in a number so close to 0. Because that's what this number is. So if we actually changed this number and put it in scientific notation, from scientific notation to standard, we'd put a decimal point, we would end up having 4 zeros and then the 4.5173346. And if we were dealing with money, that's 0, right? That's $0 right there. So how did we find something that was so close to 1? We raised it to a power that was huge. It's a big power. And we ended up with something that's almost 0. So we're going to take a look at this problem next time and have a really nice way of showing what's happening here so that we can get a sense of what happens when we're working with decimals and exponents, okay? So we will push pause, and you don't have any homework for tonight.